Hello everybody, welcome back to Alex Does LeetCode. We have just finished our bi-weekly contest on the 23rd of December. And right now, now that the contest is over, we're going to discuss the answers. If you're just joining us, we're going to talk about the answers for questions, all the questions that we're able to answer. Well, unfortunately, this contest was surprisingly difficult. I certainly did not manage to answer all the questions. I'm hoping some of our viewers will be able to do better than me. Personally, I feel a little bit embarrassed because I'm supposed to be a LeetCode streamer, but I unfortunately don't have all the answers for you. I will continue to work on these problems on my own time, though. I will continue to work on these problems, and I'll try to come up with a video afterwards for the questions that I missed. Or for the questions, especially for the questions that people are interested in. So if there's something that you want more explanation on, then I will make a special video on that. Yeah. So personally, I think the most important part of entering this contest is not how many points you get, but really it's about what you learn. What you learn afterwards. Okay, so without further ado, let me switch my screen. Counter number of removal. Okay. So yeah, let's start with question 1. But before that, a disclaimer: I was not. Actually, first of all, before we start discussion, I'm a little bit embarrassed to say that I didn't manage to get question 3. I couldn't manage to get question 3. Even though it's very similar to question 1. On question 4, I had a bug, which I'm pretty confident I'll be able to fix given a little bit more time. But question 3, I was really stumped. For those of you who did enter the contest, feel free to spam in the chat which questions you got. I'm really hoping, I'm rooting for you guys. I hope that you guys did better than me. But for those of you who needed a little bit more help with question 1 and 2, we'll talk about that. For question 4, I'll talk about where I got to, what the bug is, and how I intend to solve it. And for question 3, I will talk a little bit about what my plan is to solve it. But question 3 was pretty hard, right? This week's contest is kind of hard for some reason. Okay, so let's start with question 1. As usual, we read the description of the problem. It says, count the number of incremovable subarrays 1. You know, the thing about LeetCode problems is that they all have these very complicated words that I don't understand. And the contest, they have very long descriptions, which is a pain to read because English is not my first language. So I'm struggling with the English already. But it's okay, we have numbers, we have pictures, and that will guide us along. It says here, you're given a 0-day index array of positive numbers. A subarray is incremovable if nums become strictly increasing when you remove the subarray. So for instance, 5, 3, 4, 6, 7. If you remove 3 and 4, then this becomes 5, 6, and 7. So removing 3 and 4 makes the array increasing. And this means that 3 and 4 is incremovable. If you remove 5, you get 3, 4, 5, 6, and 7. So 5, just 5, is also incremovable. So that's what incremovable means. Examples they give, 1, 2, 3, 4 is 10. Basically, whatever you remove or don't remove, you get an incremovable array. You cannot select an empty subarray, that's fine. 6, 5, 7, 8. So you remove 5, you're done. You remove 6, you're done. You move 5 and 7, you're done. So these are the different options for making the array incremovable. So Anshu, we can't jump to the third question, but I will get to that. So I do have to tell you though that I didn't manage to do the third question. So if that's the only one that you're interested in, unfortunately I don't have the answers for you. I will think about it a little bit more. I might come up with a video at a later time if I come up with the answers, but I apologize for that. No promises. For example 3, same thing, so 8766. If you remove 8766, note that 87 is not incremovable, because if you remove 8 and 7, you're left with 66. And the rule says we want the array left to be strictly increasing. Yeah, sorry about that, Anshu, but hang out, stick around if you want to just chat. By the way, for folks who did get the answer, feel free to talk in chat if you have an even better solution than me, right? I'm more than happy to hear that. So 66 is not strictly increasing, so removing 87 will not help. So this problem, when you look at a problem like this, it's very tempting. Like I do a lot of LeetCode, so it's very tempting for my brain to immediately say, how do I do better, right? How do I get the clever solution? Where do I get the dynamic programming solution, right? But the truth is, this problem, if you look at the constraints, the size of the array is only 50. This means that you can use a brute force solution to solve it. The most simple, most direct solution. Well, let's do this. We'll generate all possible combinations of subarrays. We'll remove them and see if we're left with something that works, right? So we have like 3, 5, 7, 4. So let's generate all possible combinations of subarrays. Let's try removing 5, removing 3, removing 4, 6. Let's say, or remove 3, 4, 6, and see what happens, right? We'll generate all these combinations, all possible combinations of subarrays that we can remove. And then we see if the array that's left follows the constraint of being strictly increasing. So the way to do that, the way I did it is just as good programming practice. It's good to put things in a separate function, right? Put sort of bits of logic that is standalone in a separate function. So to do that, I essentially use a nested for loop to generate all possible subarrays. How do you generate that? Well, you have a start and you have n pointer. The start pointer goes from 0 to n minus 1. The end pointer goes from the start pointer plus 1. Right? You have an array. Your start pointer is here. Your end pointer cannot be here, so it has to be afterwards. And then this to here is what you're going to remove. Right? So that's basically the plan. That's going to be the plan. So we are going to generate all possible subarrays using these 2 pointers. And then what we're going to do is we're going to check. We're going to write a function that will check. So this function says, given an array, we're going to check if this array is strictly increasing. And the way we do that is, well, very simple. We use a for loop. If the length of the array is 0, yes, we're good to go. If the length of array is larger than, actually this should be like 0 or 1, to make it a little bit faster, but it doesn't matter. If the length of array is larger than 1, then what we want to do is to check every pairs, every adjacent pair, nums I plus 1. If it violates the constraint, the one on the left is larger than the one on the right, return false. If not, return true, right? This is a pretty straightforward array, a for loop that you've written a bunch of times, just to check pairs of adjacent numbers. Okay, so the only thing that is, I think, a little bit interesting about this solution is this little incantation here. You solve it so good, I will give you free rice. Thank you, Saba, for free rice. I don't know if I did good though, because I want to have a disclaimer. I couldn't get question 3. Many of you also couldn't get question 3, but as a streamer, I feel really bad that I couldn't get question 3. But thank you for your free rice anyway. Rice is my favorite. Okay, so here is this weird incantation here. So what this thing does is that it does slicing, right? If you're not familiar with slicing, I don't know whether I should do a video. If you're not familiar with slicing, comment or write in the chat, and then I will release a video on slicing to explain how slicing works. Basically, this notation says take nums, the list, but go from item 0 to item A. So technically item A minus 1. Right? So same thing. Take B, go from item nums, go from item B to the end. There's nothing here, which means the end. So what that means is that for an array, like A is here, and then B is here, nums 0, A will be this one. And then this one will be nums B colon the end. Okay, so this is what it's saying. So this essentially ignores this. So it takes this piece here. Let's use a different color. It takes this piece here plus this piece here. Right. So this one is a little fun little notation. I think that's the only thing that's interesting about this problem. When you run it, you get the answer. Okay. So this works because the length of the array is very small, as you're about to see. It doesn't work for the other one. Yeah, somebody solved the question in six and a half minutes. I'm very impressed in that. Next time, I will look at his live stream. So let's look at the second problem, right? So the second problem is find polygon with the largest perimeter. So when I first look at this problem, basically it says you are given a number of positive integers of length n. You're supposed to pick as many integers as you can and use them to construct a polygon with k sides. So for instance, if you're given 5, 5, 5, the only thing you can make from this is a triangle with 3 sides, and its maximum perimeter is 15. Okay? Let's look at this other one. Nums 1, 12, 1, 2, 5, 53. Okay? So, given this, what is, you might think, okay, can I make a 1, 2, 3, 4, 5, 6, 7, a heptagon, a 7-sided polygon with all the numbers here? Well, it turns out you can't. You're not able to do that because 50 is larger than all the other numbers here. So think about why is this constraint important, right? This constraint right here. The longer side of a polygon is smaller than the sum of its other sides. Why is this important? Well, imagine if you have a triangle, right? If one side is 10 and its two other sides are 2, well, it's not able to close the triangle. It's not able to close the triangle. Because these 2 plus 2 is only 4. So even if you put them all in a straight line, like these two edges, these two sides will not be able to close it up. Right? So that's why there's a constraint here. The longer side of a polygon is smaller than the sum of all its other sides. Yep. So that's the constraint that we're working with. The other constraint we have that's sort of implicit is that a closed plane figure has at least 3 sides. So we're looking specifically for a polygon with at least 3 sides, and the longest side is smaller than the sum of the other sides. These are the only 2 constraints we're looking at. So when I read this problem, I felt it was really tempting to think of this as a polygon problem, right? Like a math geometry problem. But the truth is, it's not. It is just a simple arithmetic problem where you have to deal with these 2 constraints. Constraint 1, constraint 2. And if you have these 2 constraints, you're done. Right? And so basically, you want to take this for example, you want to pick out as many numbers from here such that no one number is larger than the sum of all the other numbers. Okay? No one number is larger than all the sum of all the other numbers. So 50 here, if there's a side with 50, then all the other numbers added together, will not be able to close this polygon. So that's the problem we have. So how do you do that? Basically, the best way to do it is just to sort this. You take this list and then you sort it in ascending order, and then you check the largest one, right? Does the largest one violate the constraint? If it does, drop it. And after we drop the largest one, what happens? We get 112, 1, 2, 5, 3. Hey, now 12 is the largest one. Let's check if 12 violates the constraint. So if 12 is here, the other numbers added together actually gives it 12 exactly. So 1, 1, 2, 3, 5, right? So this means that this also violates the constraint. 12 also violates the constraint. Essentially, what we have to do is to keep removing the biggest number until we end up with something that works. And so now so if we forget all the things about polygons, yeah, this is not very nice. I see some not very nice comments on the chat. I am going to remove people. I am going to have to remove people. Well, if you want to come to a chat, I'm going to ask you to be nice. Be nice to people. Be nice to each other, and also be a little bit kind to me. You don't have to be nice to me, but just don't, no racism, right? No racism is allowed on this channel or in YouTube or in life in general. Okay, so our strategy here is basically we're going to take the list, we'll find the largest number, and we're going to repeatedly remove it until we get to a point where the largest number is smaller than the sum of everything else smaller than it. So this is the strategy here. We're going to sort these numbers. We're going to say while length of nums larger than or equals 3, if it's smaller than 3, right? If it ends up at any point we have less than 3 numbers, then we return -1. While we're going to look at the last number. So again, this is sort of Python specific slicing notation. Nums -1 give us the last number right at the end. This will be the biggest number. If nums -1 is larger or equal, if it's larger than equal to the sum of all the other numbers. So this is again slicing notation. If you're not familiar with the notation, comment, put it in the comments, write in the chat. Let me know. I will put out a video just on slicing. And you do nums equals to nums :-1. This would remove the last element. Okay, and then you keep doing that until you agree with this constraint, and then you break, and then you return sums of nums. So this one I think is not. This might be even easier than the first problem, I think. There's a question. In slicing possible in C++? No, unfortunately not. Slicing is basically like a syntactic notation. C++ is a very old language, so its syntax is a little bit more old-fashioned, and it doesn't contain slicing. I want to say that it's a Python specific notation, but I'm pretty sure there are other languages, modern languages especially, that might contain something similar. Yeah, if you know of something like that, put it in the comments, put it in the chat. Alright, so question 3. So this is sort of this is my most unhappiest question. And like I said, I'm sorry for those of you who are looking forward to hearing the answer. Unfortunately, I was stumped also. If you read the question, it looks exactly the same as question 1. But if you take the solution from question 1 and you stick it in and you run it, you actually get a timeout. It's charging. It's going to time out soon. Time limit exceeded. And the reason for that is in question 1, if we look at the constraints, the maximum length of the array is 50. The maximum is 50, whereas this one is 10 to the power of 5, which is 10,000. This is huge. In question 1, we did ON square. ON cube actually. ON cube algorithm. So we have a nested loop here. So this is ON square, and this check here is another loop that gives us ON cube, 3 loops nested within each other. And apparently ON cube is too slow for array of size 10,000. So I'm very intrigued by this question. I'm gonna think about it a little bit more by myself. If people are interested, I might release an extra video, just like I released an extra video on question 4 from the last contest. The way I think about it right now, so here's how I'm thinking about it. Here's the way I'm thinking about it, right? Essentially, we're generating all possible combinations, and then we're checking them. But the thing is this. If I see, let's say this is 10. Oh, oops. Let's say this is 10, and this is 5. Then I know that this is already a problem, right? So any subarray that doesn't remove this 10 and 5, or doesn't remove something around it, will not work. I have to remove at least one of these, right? I have to remove either this one or this one. And even removing them, even if I remove 5, it still might not work, because like this can be a 6, right? And then this 6 and a 10 would be a violation again. But the thing is, this means that I don't have to check like this one, right? I don't have to check like this subarray or this subarray, because any subarray that doesn't touch this is going to fail. Any subarray that doesn't touch these numbers in the middle are going to fail. So I think there's a way to at least make this n square, I want to say. I'm not sure. I'm going to think about it a little bit. I am going to think about it a little bit. I think that's the way to make this much faster. There might be a way, there might even be a way. So this is like one sort of train of thought that I have. The other way that I have is, you know what? Let's not get super complicated. Let's keep this structure, but we want to make the check O1 instead of ON. And maybe n square will work. Because n cube doesn't work, maybe n square will work. I need to find a way to make check O1. Maybe there's a way to do that. And the reason is, once again, you know where the hotspots are. You know where the problematic parts of the array are. So maybe there's a way to check, if like right away in O1 time, if the range that we have covers all the problematic hotspots of the array. So I think about it a little bit. Unfortunately, I'm sorry this didn't work out. It was a very hard week. I do hope that you guys did a little bit better than I did. And we'll come back to it. Okay, so let's go on to question 4. Question 4, find the number of coins to place in 3 nodes. Okay, so for those of you who tried this problem, so my biggest gripe with this problem is that it takes more time to read this and figure out what the heck is going on than actually doing the problem. This is a very complicated problem. The solution is complicated too, but the problem definition is super complicated. But let's go one step at a time so that everybody understands what this problem is asking for. Okay, so it says here you have a undirected tree with n nodes from 0 to n minus 1 rooted at 0. Okay, this thing is actually super important. You're given a two-dimensional integer array edges of length n minus 1 where edges I equals to ai bi. Indicate there's a connection between these two things. Okay, so this constraint, if you know your graph theory, this constraint means that as long as the graph is connected, as long as this is not a graph that is like broken up into pieces, this would definitely form a tree. This is guaranteed to form a tree, right? Because essentially every node other than except one node, you have n nodes, right? So every node except one node has an edge to it, and that edge connects to its parent. So this is guarantee. This n minus 1 thing guarantees that this is going to form a tree. It's not going to form a DAG. It's not going to form a graph. There will be no cycles in this tree. This tree is also rooted at 0. Okay, so the second part says, that there is a thing called cost, which is the cost assigned to the ith node. Okay, fine. So far, so good. Now, you're going to suppose to place some coins. You're supposed to place some coins on the nodes as follows. And this part was a little bit confusing. I had to read it like 5 times to understand what it's talking about. So basically it says, well, if the size of the subtree is less than 3, then place 1 coin. If the size of the subtree is greater than 3, then find the 3 biggest nodes, multiply them together, the maximum product of cost values assigned to 3 distinct nodes, and if that is negative, put 0, otherwise it will be that number of coins. Okay, so this to me is a lot of words, but let's see in action. So here's the first example. So you have edges 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. So that constructs this 0, 1, 0, 2, 0, 3, 0, 4, 0, 5. Right? These are the edges. These edges will construct the tree. The cost is 1, 2, 3, 4, 5, 6. So the cost doesn't appear in this diagram. It's basically 1, 2, 3, 4, 5, 6. Okay? And then what you want to do is find coins. Like this is a little bit confusing for me. I want to find coins, right? So the rule is, if for every node, if this node has less than 3 subtrees, 3 nodes in a subtree, then place 1 coin. So this guy has nobody in his subtree, right? It's just itself. So we can guess 1 coin, 1 coin, same 1 coin, 1 coin, 1 coin. And this guy has 1, 2, 3, 4, 5, 6. It has 6 things, including itself in his subtree. All right, this whole thing is his subtree of 0. So, 0 has 1, 2, 3, 4, 5, 6. You look at the values. So look at the red numbers. And you pick the 3. You pick any combination of them. So for now, we're just going to say 3 biggest ones. That's actually not true. But let's say take the 3 biggest one, multiply them together. 4, 5 times 5 times 6. This will give us 120 coins. So it's very confusing. Every node, so think of a tree, every node has 2 numbers associated with it. It has a value which is given to you and a coin which you're supposed to calculate. the value or cost is given to you in this array here. Oh, sorry. Literally not that array here. It's this red array here. And then the coins you're supposed to calculate is this blue thing that underline. Okay? So every node has two things associated with it. Okay, so let's look at another example. Okay, so this one again constructs a subtree. These edges, they have costs associated with it. So it's 1, 4, 2, 3, 5, 7, 8, minus 4, and 2. Aha! Minus numbers start coming in, and that's a little bit tricky. Okay, but it's not that tricky. So same thing. We start with we start by looking at all those guys who have less than 3 things in their subtree. So this is going to be 1 coin each, because they're the only ones in the subtree. They have less than 3 nodes in their subtree. This guy, look at this guy, number 4 here. Let's use a different color, just for fun. Look at number 4 here. His subtree is this one, right? So 4 has 4, 3, 5, and 7. And if we want to pick 3 numbers here to get the biggest answer, then we're going to pick 4, 5, and 7. We multiply them together. And this will give us 140. 4 times 5 times 7. What about this other guy? So similarly for 2, the 3 biggest numbers here we have are 8, 2, and 2. When we multiply them together, they'll give us 32. And let's look at the one on top. Okay, for 0, everybody is in his subtree. So we can pick any numbers here, any 3 numbers here, multiply them together. So we're gonna for here we're gonna pick the 3 biggest ones, which would be 7, 8, and 5, 4, and 7, 5. Yeah, 7, 8, and 5. So this gives us 280. Okay, so that's how the question works. That's how the question works. So note that these coins cannot be smaller than 0. 3 maximum costs, 5 basic. Okay, let me read my chat real quick. Hello DreamWorks, welcome to the channel. Welcome. If we keep track of 2 things for each node, the size of the subtree, maximum 3 costs for each subtree. We give if else and output. Okay, read it, man implementation. I can't figure out for maximum 3 costs. We can find maximum 2 costs, but what about 3 maximum costs? Not quite sure. Okay, I'm not quite sure if this is a question. So the maximum 3 costs is basically you find the sort of biggest numbers and you multiply them together. But because they have the positive, you have to watch out for the sign. That's all. You either find the 3 biggest positive numbers, multiply them together, or you find the 2 biggest negative numbers and multiply that with the biggest positive. So these are there are only 2 ways you can get a positive number. Okay. So I'm going to talk about how I implemented it and what the pitfalls are. I actually ran out of time. Towards the end, I found that there was a bug in the way I thought about the subtree, the problem. I didn't realize this about the problem until much later. So I didn't understand the problem fully. But I'll explain how I implemented it. Basically, what I did was I did it as a tree. I actually rendered the tree. This is I don't think this is the most optimal way to do it. I think there are easier ways to do it. But because I didn't have time, I just did it this way. So the way I rendered the tree is as follows. I created a class called treeNode. I have index, value, children. I end up not using the parent, but the usual things you'll find in a tree. The value is this red number here, right? This red number is the value that's given to you. And then the index is basically the index of the tree, because I have to keep track of what the node is. So the way I actually did this, which turns out to not be exactly right, because I made assumptions about the problem, is it's here. So I started by creating all nodes, a bunch of empty nodes. So this is, again, as you can tell, I am a fan of using very Pythonic syntax, and I definitely encourage you, if you want to use Python as your main language for programming, either for like LeetCode type problems, or if you want to become a ML engineer or data engineer, you should learn Pythonic notation. This is much easier to read. What this particular thing is doing is that it says for I in range n, I'm going to create a tree node. Its index is I, and its costs, its value is cost I, right? So I fill in these two numbers, its index and its cost. So it will be this oh, I lost my drawing. So the red number plus the index. Okay, so that's what I'm doing here. And then next step I do is basically to fill in the tree. So for each edge, I connect edge 0 dot children plus equals edge 1. So for each edge here, for each of these edges, I connect this as the parent to this child. Sounds innocuous enough, but I'm going to put a exclamation mark. This isn't exactly right. I'll come back to it and discuss why. Okay, so the next thing I did was for nodes in nodes. Okay, so once I've done that, I basically use a brute force solution, right? I think, again, there should be a better way of doing this. I might release a video later on. I just ran out of time to sort of do the better way. Essentially, after constructing the tree, using the tree node class that I wrote, for each node, I got its subtree. So to answer an earlier question in the chat, is recursion the best way of doing it? I'm pretty sure it's not, but this is the way I did it. So I just did if length of children equals 0, return node val, else find recursively find the node val of all the children, and then add it to result and then return result. So this function basically recursively goes down the list and returns all the nodes of the children. So this is not the best way to do it. I'm pretty sure I should be able to do this sort of en masse. In fact, I can do this using dynamic programming. I can change 2 lines here and make it better. But maybe I'll do that later. Yeah, maybe I'll explain the solution first. So yeah, after I get all the values, so essentially that's the step here where for 0 I'll collect, let's say for 0 I'll collect all these values under them. I should not have erased that. All these values, 1, 4, 2, 3, 5, 7, 8, minus 4, 2. Right? I'm going to collect all these values under them, find the largest ones, and then multiply them together. So initially, you collect all the values, you sort them, and then If they are less than 3, then coins equals to 1. If not, then you take the max of 0 and the sort of 3 largest. Again, Pythonic notation. Once I sort all values, I'm going to take the last 3 numbers will be my 3 biggest numbers. Okay, that when I ran this, so initially I did it this way. I said, multiply the 3 biggest numbers together. And if that's less than 0, then, well, sucks. Max 0. I realized that actually was not correct because okay, so for instance, this turns out not to be correct because let's say these are all the numbers that you have in your subtree. You want to find the 3 biggest. You want to find 3 of these numbers that will give you the biggest product, right? To give you the biggest possible product. You might instinctively say, well, the biggest product is basically take the 3 biggest numbers and multiply them together. So you take the 3 biggest number, 1 times 1 times 1 gives you 2. And you think, oh wow, this is the biggest product. That's actually not true. The truth is, you can either take 3, you want to multiply 3 things together, A times B times C, and you want these 3 things to be huge. Either all 3 are positive numbers or 2 of them are negative numbers. So the other way the other triplet that you can consider is actually 10 minus 2 and 2. So this actually gives you 40. Even though there are 2 negative numbers here, because there are exactly two negative numbers, they cancel each other out in terms of sign. And this will give you a big positive number, right? So this means that in addition to checking the 3 biggest number, I also have to check the 2 smallest numbers, which will probably be negative, and the biggest one. And I don't care about the sign. I don't have to check, worry about the sign. If the sign is wrong, that just means I get a smaller number, right? This like max would sort itself out. I don't have to worry about sign. And after that, I just return. After that, I put in coins and I return that, right? And return this. For n in nodes, return n coins. This will give me an array of all the coins attributes in nodes. And so, when I ran this, I thought I got it right. I'm pretty sure I got it almost right. It's still judging. It's almost right. But there's something that I realized I had assumed that was actually not true. So when I constructed my tree, basically I made the assumption that for every pair of edges, the one on the left is the parent, and the one on the right is the child. This is not actually the case, because as you can see in this one, we're going to go through it. 0, we have 2. Okay, 0, 2, parent, child. So far, so good. 0, 6, parent, child. So far, so good. Okay, let me see. What else is... Where are my other 2's? There are no other 2's. Okay, 6. So 6, 7. Okay, 6, 7. Already there's a violation. Already there's a violation of my assumption. I assume that pair 7, because it appears because 7 appears on the left, I assume that it's the parent and 6 is the child, but I was wrong. That's not how the problem interprets the graph, right? That's not how the problem interprets the edges. It might be backwards. I have to be careful about this. Same thing, 3 and 6. So 3 is the child, 6 is the parent. The order doesn't imply anything. And then we just continue it out. 3 is 1 and 9. You see, these are all backwards. And then 1 is 8. 3 is 6. 3 and 5. Oh, they're all 3s. And 5, and then 1 and 4. Okay? So they're all backwards. So the only reason how I know this is 3 is because the number of edges is n minus 1. And so, you know, if you apply graph theory, you know that this will not give you any cycles as long as the graph is fully connected. Yeah. So so that's something that I still have to fix for this problem. Essentially, what I have to do is, instead of doing the easy way down here, easy way of just doing this, I have to actually do this recursively. I have to say, well, start from 0, add 2, add 6, and then look at what are the children of 2. Well, the children of 2, let's look at anybody else with 2 in it. Nope, nobody else. Anybody else with 6 in it? Well, there's 6 here, and then so on and so forth. So I actually have to do it the hard way. Okay, so that's something that I need to fix. I'm going to fix it, and I'm going to retry in this problem. The other thing I need to fix is actually this recursive solution here. Somebody asked me if this recursive, I don't know if this is what they were asking for. You know, this recursive solution, is it the best way to do it? It's actually not the best way to do it. The best way is a dynamic programming solution, which means that instead of returning instead of returning this right away, I'll say node dot I'll use some kind of memoization. Actually, I just use a memoization table. If node dot has self dot child values equals to none. Oh, actually shouldn't be equals to none. I'll just do it like this. Dot child values equals to none. Return. So this would not change how my function works, but it'll make it much faster. Node dot child values equals to this. So this would remember. It'll remember what the lower nodes are. So this way we only calculate child values for each node exactly once. So previously I was calculating child value a large number of times, repeatedly for the same node. Equals to res. Okay, return res. Okay, I'm pretty sure this will work. Well, it's not work. I still have to solve the other problem, but I'm pretty sure that this will be a faster version of the same program I wrote. Yeah, so it got stuck in the same place. So I need to solve this. So this is actually a slightly harder problem. I have to think about it a little bit. But you know, that's all for today. Sorry once again, guys, for question 3. If you know the answer, or you have a better solution than I am, feel free to write in the comments, right? This is a learning channel for everybody. If you know something that we don't, feel free to share it with the rest of us. I'm more than happy for you to do that on my stream. That's all that's all the time I have with you today. Thank you very much for joining me, and ciao, see you next time.